Good morning, fellow material scientists, and welcome to another video on this channel. Today I'll be talking about high temperature nanoindentation, and the focus will be on implementation and overall the challenges that might occur. So without further ado, let's dive right into it. First, I would like to show the schematic layout of a nanoindentation system and start by explaining the basics of nanoindentation. So nanoindentation is our go-to technique for measuring mechanical properties like hardness or even Young's modulus on a micro scale, of course, right? So we use like a hard, sharp indenter, usually a Berkovich tip. It's made out of diamond, and it gives you like the three-sided pyramid, as you can see. And now we apply controlled load and measure then the resulting penetration depth. And what we're after is the load displacement curve. From there we can use the Oliver-Farr method to obtain the Young's modulus, for example, or even the hardness of our material. Now that we've talked about nanoindentation in general, we might ask ourselves what happens if we increase the temperature. And I think Richard Feynman explained it a little bit better, what happens if you apply heat to a system.
Carbon atoms, and they jiggle and they make mothers jiggle, and you get a terrible catastrophe.
So at those elevated temperatures, the true nature of the material begins to show through, and mechanisms like creep, phase transformation, and diffusion can occur, and those can dramatically alter the performance of the material. Unlike room temperature testing, those high temperature conditions reveal behaviors that are time-dependent, nonlinear, and often unpredictable and sneaky. So we need high temperature nanoindentation to prevent those terrible catastrophes, like Richard Feynman said, from happening. High temperature nanoindentation provides a powerful way to probe these effects at small scales, allowing us to study creep resistance, thermal softening, and even time-dependent plasticity. Understanding those behaviors is crucial for designing materials that are used in jet turbine blades, nuclear reactors, and even microelectronic devices. And in those applications, failure under extreme conditions is not an option at all. So after all, we don't want a jet engine that's just vibing at over 1000 degrees Celsius. And that's why we need high temperature nanoindentation to study the mechanical properties of our material at high temperatures. So now I would like to talk about the challenges that occur during high temperature nanoindentation. Due to those elevated temperatures, thermal drift will occur. What does thermal drift even mean? Thermal drift refers to the slow movement or expansion of parts in a nanoindentation system, for example the tip, due to the temperature changes over time, which will then lead to an inaccuracy in the displacement readings, meaning maybe there's a displacement shown or measured when there's actually no movement at all happening. Now, to be a little bit more specific, we have, for example, system frame drift, and that happens when the system heats up and the mechanical components also heat up and expand microscopically. So even a tiny expansion in the nanometer range can distort the measurements, especially since the nanoindentation itself is highly sensitive at small scales. And we also have contact instability, meaning that the interface between the indenter tip and the sample surface can also drift due to uneven heating or thermal mismatch between the materials, such as temperature gradients, for example. This can mimic or obscure real mechanical responses, leading to misinterpretation of material properties. So thermal drift is the unintended movement of the indenter tip due to expansion or instability caused by the heating. So to work our way around that, we can use thermal drift compensation. What can we do, for example? We can independently heat both the tip and the sample, using a laser maybe. Doing so, we can match those temperatures precisely to reduce the thermal mismatch at the contact interface. Also, we can use in situ thermocouples and the feedback from the temperature controller to keep it adjusted throughout the entire measurement. So, doing so, we get a more stable contact point and reliable displacement measurements even at high temperatures. So another problem at those elevated temperatures is oxidation. So many materials begin to oxidize quite rapidly at those elevated temperatures, which means that oxide layers form on the surface, and those layers can grow, change, or even crack during the testing. And why is this an issue? You're no longer indenting the base material, you're indenting the oxide. And those oxides, like I said, are often brittle and are misleading in terms of the mechanical response compared to the base material. And those oxide layers can interfere with thermal stability and even the tip sample contact itself. Well, what can we do to overcome this obstacle of oxidation? We could use an inert atmosphere or a vacuum. By doing so, we can significantly slow down or prevent oxidation from happening. We could also use a thin protective coating. They have to be very thin and stable at those high temperatures, maybe like silicon nitride or alumina, and those can be deposited and act as a barrier, preventing oxygen diffusion during the testing. But this only works if the coating is thin enough, meaning that the thickness of the coating has to be significantly less than the penetration depth during the indentation. Furthermore, we also have creep. Creep refers to the time-dependent deformation of a material under constant load, and that is especially present or significant at high temperatures. So how can we correct it? We can use time-based hold segments during the indentation test, where the load is held constant while the displacement is recorded. Then the system can separate creep deformation from elastic and plastic components. This is mainly done by software side that applies models to extract corrected material properties, for example, like the true hardness or even Young's modulus. So as a result, we get the accurate characterization of a material that undergoes a slow deformation under a load, like metals or even polymers at elevated temperatures. Okay, now to sum things up. What even is high temperature nanoindentation? Well, it's a technique to measure mechanical properties, such as hardness, Young's modulus, or creep, of materials at elevated temperatures at a nanoscale. Those temperatures can vary to about 800 degrees Celsius. Well, why do we use it? We want to understand material behavior under thermal stress. It's crucial for applications in aerospace, automotive, energy, and even electronics. And it also reveals creep, plasticity, and phase transitions. Now for the challenges, we have thermal drift. How do we overcome that? We want independent heating and control of the tip and the sample so that no temperature gradients are forming. At elevated temperatures, materials will oxidize. So to prevent that oxidation from happening, we can either use an inert atmosphere or vacuum, or even deposit thin protective coatings or layers on top of the material. Last but not least, we will have creep. Well, how can we work our way around that? We will use time-based hold segments, and from those we can extract creep components as well as the plastic and elastic components. This is done by software. So thanks for stopping by and watching the video. I hope you learned something about high temperature nanoindentation today. And yeah, don't forget to indent that like button and subscribe so you don't miss out on any new videos about scanning probe microscopy and its applications. With that being said, take care and stay curious.